Okay, welcome. So today we are going to continue our discussion on block codes in the morning, and in the afternoon Professor Costello will start the discussion on convolutional codes. So, so far let us do a quick recap of what we have done so far. So, we have described block codes by generator matrix and parity check matrix, and we said what is a syndrome and how syndrome can be used for error detection, as well as how we can use syndrome for decoding linear block code using standard array. Then we talked about distance properties of linear block codes, and we talked about what is a minimum distance and how random error correcting capability and error detecting capability of a code is dependent on the minimum distance of the code. Today in the morning 2 sessions, we are just going to talk about some very simple class of linear block codes. So, we will study their construction and we will study their decoding of those linear block codes. So, we will start with basically, before I do that, I will just define what is a dual code. I think Dr. Costello, to answer one question he mentioned in the yesterday about dual codes. I will formally define what is a dual code, and then I will talk about some examples of linear block codes. So, I will start off with repetition code, which you have already seen, single parity check codes and Hamming code in this lecture, and in the next lecture I will talk about Reed-Muller codes. So, we say two n tuples u and v are orthogonal if their inner product is 0. And how do we compute this inner product? So, basically we component wise we take the dot product, and that should be 0. Now, for a linear nk block code, we say there exists a dual code with the parameter n and n minus k. So, number of information bits in the original code is k, in the dual code it is n minus k. So, how are these code words defined? So, the n minus k dual code is defined as the set of all code words v that are orthogonal to the code words u in the original code. So, in other words, all the code words of the dual code, they will be orthogonal to the codes in the original code. So, that is basically the definition of a dual code, and the parameters of the dual codes are, if the original code is nk code, this will be n minus k. Now, if nk code is a linear code, then its dual is also a linear code. Let us just prove linearity. So, let us say x and y basically belongs to this dual code. So, what is the property they have? So, x and y would be orthogonal to the code words belonging to the linear block code C. So, let for every code word u which belongs to the original code word nk code word C, x and y would be orthogonal to them. And what is orthogonal? So, the dot product x dot u is 0 and y dot u will be 0. Now, let us assume then, let us do this lambda times x plus mu times y, let us take its dot product. So, then if we take its dot product, it will be lambda times x dot u plus mu times y dot u. What is x dot u? That is 0, because x belongs to the dual code and u belongs to the original nk code. Similarly, y belongs to the dual code and u belongs to the original code. So, this will be. So, then what we have shown is lambda x plus mu y is orthogonal to u, and what is u? U belongs to C. So, what we have shown is lambda x plus mu y belongs to CD, the dual code, right. And so, that proves the linearity property, because we said if x and y belong to dual code, then lambda x plus mu y also belongs to basically dual code. So, we have proved the linearity property that if you remember, we have said if V1, V2 are two code words, then V1 plus V2 is also a valid code word. What we have shown is if x and y is belongs to dual code, then lambda x plus mu y also belongs to the dual code. So, we have proved the linearity property of the dual code. So, if the original code is linear, then its dual is also a linear. Now, as Dr. Costello mentioned in the yesterday's lecture, we are interested to study dual code for variety of reasons. He talked about one reason in the last class, which was decoding. So, you see the parameters of these codes. This is an nk code and this is n minus code. Let's assume that like k is very large, n is also very large, let's say. Okay. So, if k is very large, then number of code words also will be very large, right. Now, if you look at its dual code, then if n and k, let's say, are close to each other, and so if you look at this dual code, then n minus k will be small, because I am saying k is large close to n. So, then n minus k will be small, right. So, you can see in case of dual code, if n minus k is small, then number of code words will be small. So, for example, you can do things like you can find out the weight distribution of the dual code very easily, because number of code words are small, you can just enumerate all these code words, right. Similarly, in many decoding algorithms, the complexity grows with k, number of information bits, right. So, if number of information bits is small, you can do easy decoding. Now, so the point I am trying to make is, whenever k and n are large, and let's say k is close to n, sometimes it is better to work in the dual domain. And what do I mean by work in the dual domain? Let's say I ask you to find the weight distribution of this code, nk code. Now, if k is very large, you cannot enumerate all of them, or it might be quite difficult. But if n minus k is small, then you can probably easily enumerate all possible code words and find out the weight distribution. Now, there is a theorem which relates the weight distribution of the original code with the weight distribution of the dual code, Macmillan's identity. So, what I am trying to say is, so if I, let's say, ask you to find out the weight distribution original code, what you can do is, if k is very close to n, you can instead find the weight distribution of the dual code and use this Macmillan's identity to find out the weight distribution of the original code. So, that is what he was mentioning, that sometimes it is easier to go to a different domain. So, what I am saying is, to find the weight distribution, I am initially finding the weight of the dual code and then using that to find the weight distribution of the original code. The example which he gave in the last class was about decoding. Let's say in convolutional code, you will see that usually k and n are small, and the complexity of the trellis complexity goes up with k. So, let's say there k is 3 and n is 4. Now, the dual code has, so in this case, in the trellis diagram, you will have 8 transitions going from each state. Whereas, if you look at the dual code, it will be 1-4 code. So, there will be only 2 transitions. Okay. So, it is easier to decode the code in the dual domain, and then there is a way to get back your original estimated bits from the decoding in the dual domain. So that is why we are interested in dual codes. So, and that is why I just put it up before I discuss various types of codes. I just put up this dual code because sometimes it is easier to work with the dual code than the actual code, if you are asked to find weight distribution of the code, or if you want to do decoding. Okay, that is why dual code is of interest to us. So, here I have shown basically the linear combination of x and y also is a valid dual code. So, that means this n minus k dual code is a linear code. Now, second property which I am going to show is, let C be a linear code with generator matrix G, and if X belongs to the dual code, if and only if X G transpose is 0. In other words, I am saying that generator matrix of the original code is actually parity check matrix for the dual code, or the parity check matrix of the original code is generator matrix of the dual code. So, generator matrix is a k cross n matrix, right. So, these are your k rows, I am denoting by G0, G1, G2, Gk minus 1, and each of them are n tuple basically, and I can use these as my basis function to generate my code words. Now, what is Xg transpose? Xg transpose, so you take basically transpose of G, and you take Xg transpose will be then dot product of X with G0, X with G1, X with G2, X with Gk minus 1. Now, I am saying if X belongs to the dual code, then Xgi is 0 for every I. Can you tell me why? Exactly. We said that dual code has this property that if you take a code word in the original code and you take a code word in the dual code, their dot product is 0. Now, look at the generator matrix. How do we generate code words? We generate code words by linear combination of these codes. For example, this code C is U0, G0, original code is in this code, in this linear block code C. If I have to generate code words, that will be V will be U0, G0 plus U1, G1 plus UK minus 1, GK minus 1. Let us say I make except U0 all 0, my code word is G0. So, G0 is a valid code, G0, G1, G2, GK minus 1, these are all valid code words in original code. So, they will be orthogonal to a code word in dual code. So, this follows from the definition of dual code. How did we define? Again, if you go back, we said that n minus k dual code is defined as set of all code words that are orthogonal to the code words belonging to the original code. And what U, as I said, the original code words U, I can write it in terms of linear combination of these generator, this basis function for the generator matrix, right. Is this clear? So, the point I am trying to make is this code which belongs to C, this can be written as some linear combination of, let us say U0, G0 plus U1, G1 plus UK minus 1, GK minus 1. So, if let us say U0 is 1 and others are all 0, what is your code word? G0. So, G0 is a valid code word belonging to C. Similarly, G1 is a valid code word belonging to C. G2 is a valid code word. So, if these are valid code word linear block code C, then they should be orthogonal to the code word which belongs to the dual code. This is from the definition of dual code. So, that is why G dot Gi is 0. So, all of these are 0. So, what we get is Xg transpose is 0. So, you can see if, and we know that if X is a valid code word, then H transpose is 0. So, essentially you can see that G acts like a parity check matrix for the dual code. Now, what I wrote here is X belongs to this dual code if and only if this is so. So, if X belongs to dual code, this is true, and if this is true, then X belongs to the dual code. Basically, that's what is meant by if and only if. It holds both way. So I have shown you if X belongs to dual code, then this condition holds. Now see if we'll see if this condition holds, then X belongs to the dual code. So if this conditions hold, then X dot gi is 0 for all I, correct? And what is the code word belonging to C? That is nothing but linear combination of this gi. So if you take X dot C, this will be X dot with linear combination of this gi, which is nothing but summation over I lambda I times xi dot gi, and xi dot gi is 0 because it is given xg transpose is 0. So then what have we shown? We have shown X is orthogonal to C. So then X is a dual code. Again, I will just repeat this statement. So wherever you see this kind of thing, if and only if, it means basically it holds both. So when you are asked to prove a theorem, let's say in this case it says if C is a linear code with generator matrix G, and if says then if X belongs to dual code, if and only if xg transpose is 0, then it means two things. It means if X belongs to this dual code, then this condition holds. And second thing it means is if this condition holds, then X is a dual code. So wherever you see this kind of statement, if and only if, you have to prove both. You have to prove first that this condition, if X belongs to this, then you show this happens, and you have to show if this happens, then this is true. So that's what we did. In the first case, we assumed that X belongs to the dual code, and then we showed that since X belongs to dual code, these were all 0, so that's why xg transpose is 0. Next, in the next case, we showed this xg transpose is 0, then we showed that then these X is orthogonal to original code word C, so then X belongs to the dual code. Okay. So what we have shown is the generator matrix of a linear NK code is actually a parity check matrix of a dual code and vice versa. Now there is a special class of dual code where the generator matrix and the parity check matrix both are same. So that is known as self dual code. So linear block code is equal to its dual code. So clearly you can make out that in this case k has to be n by 2, because k has to be equal to n minus k. So k comes out to be n by 2. So it's self dual code has to be like n has to be even for the self dual code. And so rate of a self dual code is half. Then the dual original code is rate half, dual code is also rate half. I also mentioned this. We are not going to study Gole code, but I just gave an example of a self dual code. Okay. Now let's move to some examples of linear block codes. The simplest code which one could think of is repetition code. So repetition code of length n is a n1 linear block code. Why? Because in case of a binary repetition code, maybe I should write, I by default assume input is binary. So unless otherwise stated, I mean binary code. Okay. So binary repetition code of length n is of this parameter, length is n and k is 1. So there are only one input, which can be 0 or 1, basically one bit input, right? And what are the code words for a repetition code? So it consists of two code words. For 0, all 0 sequence of length n, and for 1, all 1 sequence of length 1. Now how do you generate this code word? The generator matrix is given by this generator matrix of a, so we are repeating it. So what will be generator matrix? Huh? Exactly. So G will be 1, 1, this repeated n times, right? That's what is my generator matrix. Now, so you know how to generate codes, code words using repetition code. Now, how do you decode them? Majority logic decision. What do you mean by majority logic decision? So, you look at what are the majority of the bits are saying. If they are saying 0, you decide in favor of 0. If they are saying 1, you decide in favor of 1. If you recall the example of rate 1/3 repetition code that we did in the class yesterday, and we showed for one single error, we are able to correct this error, right? We said that that is single error correcting code, and that is because our decision was based on majority logic decoding. Minimum distance is the minimum weight of a non-zero code word. In this case, there is only code word corresponding to 1. So, basically it will be n. Now, the second code I am going to talk about is a single parity check code. Again, a very simple code, but interesting applications. So, as the name suggests, in single parity check code, we are adding one parity bit. So, if your information length is k, n is k plus 1. So, this is a single parity check. And how do we create a single parity check? So, if your information bit is u0, u1, u2, uk minus 1, then the parity bit that you are adding is nothing but modulo sum of all the information bits. So, if the number of information bits are like number of ones in the information sequence is odd, p will be 1, and if the number of ones in information sequence is even, p will be 0. So, in other words, so what will be the overall weight of this code word? Will it be even or odd? Even. So, you can see basically this will result in even weight code words. Now, I can write my code word of this form. This is a single parity check bit, and these are my information bits. So, if I write corresponding generator matrix, now from here how do I get my generator matrix? I know V is equal to U times G, right? I know my V is U times G, and V will be V0 to Vn minus 1, and this will be U0 to Uk minus 1, and then multiplied by G. So, if you look at first bit, which is P, this is U0 plus U1 plus U2 plus Uk minus 1. So, that is why it is all 1. What is second bit? Second bit is U0. So, that is this one is 1, others are 0. Third bit is U1, so it is 0, 1, others are 0. Okay. So, you can backtrack and get your generator matrix. I think Professor Costello did one example in his lecture to generate this generator matrix from these code words. You can generate this. Okay. So, that is how we get this generator matrix. Okay. Does this generator matrix look familiar? What is the parity check matrix of a repetition code? Parity check matrix of a repetition code. If you go back, this is a systematic, right? I and P, or you can write P and I, whatever you want to say. If you put it in you draw the H matrix of this, how will it look like? This will look like this. And code parameters also, that was N1 code, this is N minus 1 code. In fact, and again from here also I can get the this is some matrix P, and this is identity matrix. So, if this is in the systematic form, so I can write the H matrix as I and P transpose. So, H will come out to be this. And the interesting part about this single parity check code is all code words are of even weight. So, this can detect actually all odd weights. What is the minimum distance of this code? You have your H in front of you. Exactly, because 2 columns add up to 0. So, the minimum distance is 2. So, if the minimum distance is 2, how many errors can it detect? 1, right? And how many errors can it correct? 0. It cannot correct any error. So, minimum distance of this code is 2. But the beauty about this code is, see, it cannot guaranteed to correct any error, right, because minimum distance is 2, and it can detect, guaranteed to detect 1 error. But it can actually detect, even though its minimum distance is 2, it can detect actually all odd weight errors. So, it can detect errors of weight 3, weight 5, because it has this nice property that all code words are of even weight. And this single parity check and repetition codes are dual to each other. You can see basically the code parameters, and these H and G are, H of this matrix is G of that matrix. So, these are dual of each other. The next code I am going to talk about is Hamming codes. Now, Hamming codes are single error correcting codes, and these are the parameters of these Hamming code. So, for m greater than equal to 3, there exists an Hamming code with following parameters: n given by 2 raised to the power m minus 1, k given by 2 raised to the power m minus 1, the number of parity bits given by n minus k, which is m, and it is a single error correcting code which has t equal to 1 and minimum distance given by 3. So, you can see once I fixed my m, my code parameters here are fixed. My n is fixed, k is fixed. Okay. So, once I fixed my m, then the parameters of my Hamming code are fixed. Okay. Now, to describe this, we need to first mention how to generate this code word, or we need to describe the H matrix. So, the H matrix of this Hamming code has a very simple form. And what is that? So, now what are the dimensions of the H matrix? This is n minus k cross n, right? N minus k cross n. Now, if you look at here, n minus k is m, and n is 2 raised to the power m minus 1. So, the parity check matrix has m rows and 2 raised to the power m minus 1 columns. So, can you guess what are the entries of the, what are the columns of H matrix? These are nothing but all non-zero m tuples, because we need n columns, which is 2 raised to the power m minus 1. So, if you take all non-zero m tuples and put them as columns of this H matrix, that is your parity check matrix for Hamming code. So, it is very easy to remember the parity check matrix of the Hamming code. So, once you fix your m, then you put all m tuples. So, for example, if I fix my m to be 3, if I fix my m to be 3, okay, then I enumerate all possible 3 tuple. So, if m is 3, what is n? 7. So, this will be 1 0 0 0 1 0 let us say 1 1 0, 0 0 1, 1 0 1, 1 1 0, 1 1 1. This is basically your 3 cross 7 H matrix. Now, if you want to put it in the systematic form, I wrote it like this. So, what you do is you write identity matrix. So, identity matrix will take care of all m tuples that are weight 1, right. And then I wrote PT consists of all m tuples of weight 2 or more. So, if you want to write, so if I want to write this in the systematic form, what I would have done was I would have done this, and then the remaining ones. So, let us say 1 1 0, 1 0 1, 1 1 0, 1 1 1. This is in the systematic form. Okay. Now, this is a parity check matrix for the Hamming code. Okay, okay. Sorry. Yes, here I have just mistake. Just a second. Where is my? Yeah. So this is which one? 1 1. Which one is this one? No. Which one is left? 0 1 1. Yeah. Here also did I repeat it? There also I repeated. Sorry. Yeah. Yeah. Okay. So is it clear what is the parity check matrix of a Hamming code? Okay. So what does the parity check matrix tells us? What information can we gather from parity check matrix? Very good. Very good. We can find minimum distance of a code from the H matrix. Now, can you go back? This was a particular example. Can you go back now and tell me why minimum distance is 2? Minimum distance is 3. So, minimum distance is 3 meaning 3 columns. So, minimum we require 3 columns to add up to 0. So, what are the entries of these H matrix? These are non-zero m tuples. Okay. You add any 2 m tuples, you get another m tuple. That is already there in the. See, all these are distinct. You agree? All these m tuples are distinct. So, if you add 2 of them, they won't add up to 0. Do you agree with this? Now, if you add any 2 m tuples, what would you get? You will get another m tuple, and that m tuple is non-zero m tuple, because these 2 m tuples who are distinct. So, when you add any 2 m tuple, you will get another m tuple which is already there in the H matrix, because we are enumerating all non-zero m tuple. So, is it clear from the H matrix that 3 columns of this H matrix will add up to 0? So, if 3 columns add up, that is the minimum required. 2 cannot add up to 0. So, 3 of them add up to 0, that minimum distance is 3, and we know that if minimum distance is 3, then it can correct t errors. 2t plus 1 is d min, so t is 1. So, from there we get these values, d min is 3 and t is 1. Is this clear? Okay. Now, I have just given an example. So, for m equal to 3, this is the length of the Hamming code, and k is given by. So, for m equal to 3, we get a 7 4 Hamming code. This is a parity check matrix, and if we put it in the systematic form, I can also get the corresponding G matrix in the systematic form, that is given by this. Now, I am going to talk about a way to decode a code which has been encoded using Hamming code. Now, there are many ways you can decode it. I will give a very simple method of decoding code using Hamming code. So, what I am suggesting is we can rearrange the columns of the parity check matrix of the Hamming code such that column in position I is the integer I. And what do I mean by this? So, let us say you can consider this as LSB, MSB, and this is the USB. Basically, this is so you read this number as 001, 012, 011. So, what is 001? That is 1. 012, that is 2. 011, that is 3. So, what I did was I rearranged the column of the H matrix in this form such that column in the ith position represent integer I. So, first column gives number 1, this gives number 2, 3, 4, 5, 6, 7. That is how I am arranging my parity check matrix of the Hamming code. Now, if your parity check matrix is arranged in this particular fashion, then we will see an interesting thing. Let R be the receive vector. So, for decoding, of course, we first have to compute the syndrome. So, let us compute the syndrome. If at most one error has occurred, the syndrome would be either 0 vector or a column of H vector. So, when will the syndrome be a 0 vector? When there is no error, okay, or undetected error. And otherwise, remember, it can correct single error. This is d min is 3. The interesting thing is, if there is at most one error, if there is an error, then the syndrome is actually the column of this H matrix, which we arranged in the order such that column I is integer I. I will give an example to illustrate this. So, whenever one error happens, the number represented by the column of the calculated syndrome is the position where the error has happened. So, syndrome will tell you a number that number tells, look at that column, that is the column where the error is. If your H matrix is arranged in the way I said, that column I should denote integer I. If you are using that H matrix, then if you compute the syndrome and single error has happened, your syndrome will be non-zero. So, whatever syndrome you get, you look at that corresponding integer and you go back and look at that is the location where the error has happened. So, when a single error happens, the number represented by the column of the calculated syndrome is the position in code word which is in error. And since we have considered binary code, so if we know which position is in error and the code is binary, so we will just flip the bit. So, let us take an example. So, we have a code word 0101010. This is a code word in 7/4 Hamming code, and what we received is 0001010. So, where is the error? Second bit. Okay. So, what are we going to do first? Compute the syndrome. So, this is our R and this H transpose, and remember H is such that this is first, second, third, this is H transpose. This is 001, 010, 011, 100. Okay. Now, what is the syndrome coming out to be? 010. What is 010? 2. And that indeed is the location where the error was. So, we know from the syndrome that error is in second bit. So, we will flip this bit, we will get back our original code. So, the number represented by the syndrome is 2 and hence the error is in second bit. So, estimated code word is given by this. Okay. Now, if you go back and look at Hamming code, now once we fix M, right, it fixes the parameter of the code. For example, when we fixed m equal to 3, we got a 7-4 Hamming code, right? But let us say you want to store data in computer as bytes. So, you would prefer to have code word length 8, right? But this cannot give you n equal to 8, because this will give only to the power m minus 1, correct? So, how can we use this construction to, let us say, get us 8-4 code? Okay. So, the point I am trying to make is, you will see these code constructions fix the size of the either code word length or information sequence length, but in many applications we may require a different n or different k. So, there are various techniques available to tweak the same design, so that to extend n by 1 or decrease n by 1 or increase k by 1, decrease k by 1. So, we are going to talk about some of these techniques next. Okay. So, the first thing that we are going to talk about is shortened Hamming code. So, how do we get a shortened Hamming code? If we delete any L columns from the parity check matrix of Hamming code, we get a shortened Hamming code. So, what happens when you delete columns? You are actually reducing n, but are you changing the number of parity bits? No, that is fixed. So, actually then deleting L columns decreases your k also and decreases your n. So, earlier your n was 2 raised to the power m minus 1, now it is 2 raised to the power m minus L minus 1. Similarly, earlier your k was 2 raised to the power m minus 1, now it is 2 raised to the power m minus L minus 1. There is no change in m, and you tell me now, earlier d min was 3, why did I write d min to be greater than equal to 3?
Depends upon the m value. If n value is 0, then it is equal to 0. If that value increases, then the d min will reduce.
Reduce, but I have it greater.
Because it is not sure that the sum of the two code values of the data.
Exactly. So, you can actually cleverly, if I ask you to shorten a code, you cleverly pick up those columns that are resulting in like minimum distance 3. So, by removing the columns, actually you can potentially increase d min, because you look for all those columns, 3 columns that are getting added up to this thing. So, if you just remove one of them, then no longer those 3. So, you are absolutely right, we can actually increase our minimum distance, because minimum distance is minimum columns of this H matrix that are adding up to 0, vector sum of them adding up to 0. So, if we cleverly pick the columns that we want to remove, we can potentially increase our minimum distance, and that is why you can actually increase. And intuitively also you can think that makes sense, you are reducing k. So, actually the fraction of parity bits are now more than what earlier it was. So, you should ideally get better performance, right? I mean, because earlier you had less fraction of bits as parity bits, now you have more. Yes?
When we can correct only one bit in any case, then what is the point in
No, so here I can, by shortening the code, actually I can correct more than, if I can increase my d min, I can correct more bits, because what was causing d min equal to 3, because we had all possible m tuples listed here, non-zero n tuples. So, whenever you add 3 of them, 2 of them will add up to the third one. Okay. So, if we can get rid of some columns, we can potentially increase d min. Okay. So, for example, if you want to decrease your n, you want to decrease your k, you will go for this method, which is called shortening of the code. Okay. So, this is 7-4 code. If I just remove one column, I will get a 6-3 Hamming code. Now, There is another way in which I can change the code parameters, which is called expurgation. So, what is an expurgated Hamming code? And again, these techniques are general: shortening, expurgation, puncturing, extension. These methods are general. I am just, since I described Hamming code, I am using Hamming code to describe some of the properties. But these shortening you can do any other. If I give you an NK code, you can shorten it by removing some columns. Yes. Limit on L. No, so what the point I am trying to make is, a particular code construction fixes the value of n and k, but in practical applications you may require some different n and k. So, the way we can design codes with those new parameters is, you design a code which is closest to those nk parameters, and then you use some of these code modification techniques I am talking about, like shortening, expurgation, lengthening, extension, puncturing. You can use these techniques to get to the code parameter. Let us say you wanted a code of 8,4 parameter, right? Hamming code would not give you that. You need to increase 1. So, 8,4 would mean that actually you are increasing 1 additional parity bit, correct? So, Hamming code would not give you. So, you can modify your Hamming code to generate that additional parity bit. By Hamming code has minimum distance 3, I can add an additional parity bit, which will ensure that I only get even parity. So, all ones in the H matrix. So, that will be 8,4 Hamming code. So, the point I am trying to make is, if I tell you, okay, give me a code of some parameters, I specify n and k. If you do not have a particular, you cannot design the codes with exact parameters, you design a code with the parameters closest to those parameters, and then you use these code modification techniques to get to those parameters. For example, if I ask you to design a 6,3 code, what you can do is, you can do a 7,4 Hamming code and then shorten it to make it a 6,3 code. So, that is what I am saying. So, this L is just a parameter I am describing to define basically how many columns you need, because when you remove L, you are decreasing k also, you are decreasing n also in case of shortening. Yes. That is a typo. Just a minute, it cannot be. That is a typo. Thanks for pointing out. So, this is actually, this is 1 1. Huh? Yeah, okay. Oh, 0 0 1 is not there? No, 0 0 1 is here. Just look at 1 is there, 2 is there, 3 is there, 3, 4, 5, 6, 7. And here I have 1, 2, I probably meant either of them. This can be like, I essentially removed one of these columns, right? I just removed, because this is there, sorry, this is, just a second, this column is here, this column is here, this column is here, okay, this column is not here, 1 0 1 is here, 0 1 1, 1 1 1 is here. So, I essentially removed either 0 1 1 or 1 1. So, there is a typo, essentially this is, you make it 1 1 0. No, 1 1 0 is already here.
0 1 1.
0 0 1 is there. You make it either 0, yeah, you make it either 0 0 1 or you make it 0 1 1. Thanks for pointing, that is a typo. Yeah, that is a typo. Okay. So, next method that we are going to talk about is what is known as expurgation. So, let C be an NK Hamming code with parity check matrix H. Now, we are defining a new code with parity check matrix given by H1, which is of the form this. So, okay. So, first tell me what is the rank of this matrix H1. If H is H has rank n minus k, what is the rank of this new matrix? And let us say H is my Hamming code. If H is a Hamming code, what is the rank of this new matrix H1? Do you have any all one rows? You do not have any all 1 rows. So, adding this row would basically the rank will increase the rank by. So, rank will be now n minus k plus 1. And what is n of this new code? Same as original code. So, then what is k? Exactly. So, k has now decreased by k has become now k minus 1. So, think about it. Earlier you had 2k code words, now you have 2k divided by 2. So, that means you expurgated, you just threw away half of these code words. And which were the half code words you threw away? So, I added this constraint, right, all once. Now, if V is a valid code word, what do you expect? V H transpose to be 0. V H 1 transpose to be 0. Now, you do V H 1 transpose to be 0, from here you will get V H transpose to be 0, and what will you get here? You will get a condition that V 0 plus V 1 plus V 2 plus V 3 plus V n minus 1 is equal to 0. And what is that condition? That your code words have even parity. So, what you did was your original code H had both even odd weight code words, you just threw away odd weight code words, you are left with only even code words. In fact, it can be proved that if C is a linear block code which has both even weight and odd weight code words, the number of even weight code words is equal to number of odd weight code words. So, what we are doing here is by adding this constraint, we are actually throwing away half of these code words. And what are these half code words, half of the code words? These are these odd weight code words that we are throwing away. Now, tell me, if this is a parity check matrix of Hamming code, what is the minimum distance of this new code H 1? Exactly, because now there is no even weight code word, I mean there is no odd weight code word, right. So, d min has to be 4. So, all d min 3 has been thrown away. So, this is a very simple way, and this makes sense. When I am throwing away some code words, so I should have bigger separation between code words, right. Think about, you have a space where you have code words there, I am throwing away half of them. So, I better get better separation between the code words. So, since a parity check matrix does not have an all 1 in any of the rows, any linear combination with the last row will never yield a all 0 vector. Hence, the dimension, the rank of this new matrix H 1 is n minus k plus 1. So, the k for this new code C 1 is k minus 1, and this is a n k minus 1 linear code. This is known as expurgated Hamming code, and as I said, we are throwing away half of these code words. Now, since the last row of this parity check matrix is all one vector, the inner product of any odd weight vector with all one vector can never be 0, because if an odd weight vector is there and you add all of them, that will give an odd weight. So, basically what we are doing is we are throwing away all odd weight vectors. So, this new code will only have even weight vector. So, earlier the minimum distance was 3, that is the minimum weight of the code. Now, we already threw away all the odd code words. So, the minimum distance would be 4. So, we have expurgated all odd code words, and now we are left with only even code words. So, the minimum distance will be 4. We have already said that the original Hamming code ensures minimum distance is 3, but since we threw away odd weight code word, now this will have a minimum distance of 4. Okay. So, this is a way of, so in this case n remains same, but k is decreased. So, for example, if I want a 7-3 Hamming code, I will use this to get a 7-3 Hamming code. Yes. This will be 4 for Hamming code, if H is Hamming code. If let us say in a general scenario, if this H has odd weight, I mean if this H has minimum distance which is odd, it will move to the next higher even weight. However, if this is already even, it may be just same, or it may just remain same. In that case, it may not change. H has d min which is odd, then this will H1 will have d min which is 1 more than what this original code had. Okay. So, this is a nice way of extending the minimum distance of a code. Let us say if you have a code which has minimum distance which is odd number, right. I mean as I said, these are techniques to change the code parameters n and k, and these are and we are interested in them because in most of the algebraic code constructions that fixes our parameters n and k, but in application we may require a different n and k. So, what we are trying to do is we are trying to design using known methods to get to an n and k which is closest to the parameters we need. Then we will apply some of these techniques to get the exact parameters. Yes. Yes. If H has minimum distance of 4, then what are you saying?
H1 has minimum distance of
4. That we can that of course, why is H has, if you are saying H has a minimum distance of 4, then you are saying 4 columns add up to 0. Now, if you are adding a 1 here and you add 4 columns, these bits will also add up to 0.
H has minimum distance 3, but it should have 4 columns which add up to 4. For H1 to have minimum distance 4.
Yes, this H has minimum distance 3. I am saying the new code H1 has minimum distance 4. I am not saying H has minimum distance.
So that H should have 4 columns which add up to.
Not H, H1.
So I am saying H1 has exactly 4. Then it should have 4 columns which add up to 4, right?
No, you are not getting the point. What I am saying is, so if I say H has minimum distance of 3, what I am saying is 3 columns, minimum 3 columns of H add up to 0. When I am saying H1 has minimum distance of 4, what I am saying is the columns of this H1 matrix, there will be at least 4 columns which will add up to 0. I am not saying, so the condition is on H. When I say H1, so condition is on the columns of this new matrix H1, and I have already showed you why it will be of minimum distance 4, because if you go back, if V is a valid code word, VH transpose should be 0. Now, if you do VH transpose is 0, so H transpose is this. So, this will be VHT transpose, and this will be get V multiplied by this all ones. Now, VH transpose is already 0 because V is valid code. Now, this would be what? V0 plus V1 plus V2 plus V3 plus V4. Now, if V or valid code word has odd number of ones, then it cannot be 0. So, we cannot have odd weight code word if your parity check matrix is of form this. That is what I said here. If you go back, since the last row of H1 is an all one vector, the inner product of any odd weight vector with all one vector is 1. It cannot be 0. So, then VH transpose cannot be 0. But we know that if V is a valid code word, VH transpose has to be 0. So, then a V which is odd weight code word cannot be a valid code word. Maybe, okay, so this is a typo, this should be V, I mean I am talking about VH1 transpose here. Is that, I don't know whether that is causing a problem here. If V is a valid code word of H1, I mean this new code C1, VH1 transpose has to be 0. So this follows from the property of the parity check matrix. If V is a valid code word, VH transpose has to be 0. And if we take VH1 transpose here, for VH transpose to be 0, V0 plus V1 plus V2 plus Vn minus 1 should add up to 0. Is your doubt clarified? So where is your doubt?
We have all one rows in the H1, right?
That's right.
So if we add 4 rows, the last is anyway.
Okay, let's just if the numbers are easy for you, I will. Let's look at this example. Okay, where is my duster? Yeah, this is my H1. H, I add 1 1. Now tell me how many rows are adding up. See for yourself.
Yeah, but are we always sure that H matrix, given matrix, 4 columns will add up to 0?
No, that depends on H.
So are we exactly sure that
Oh, you're not getting by. For Hamming, this Hamming code, we are 100% sure.
No, Hamming code, we are sure that it's 3.
Yes, not 3. This one has 4.
So H matrix has 0.
Right.
Now, when we take H1, we are saying that Hamming distance is exactly 4.
For expurgated Hamming code, yes. For if okay, I said that if H matrix has a minimum distance which is odd, then H1 will have minimum distance which is 1 more than the minimum distance of H. That is what I am saying. So since we are taking an example of a Hamming code which has minimum distance of 3, this overall code will have minimum distance 4. If this was some other code which has minimum distance 23, H1 would have given you minimum distance 24. If this would have a code which has minimum distance 99, this H1 would have minimum distance 100.
So I guess this question,
Huh?
question is a bit different. He is asking that we are guaranteed that d min will be greater than 1 plus the previous minimum distance, but will it be equal?
Will it be equal minimum distance? So okay. So let me answer this question. If you have a linear block code and that linear block code has both even and odd code word, then we can prove that number of even code words is equal to number of odd code words. Okay. So if you have a code word which has both even and odd code word, when I am doing expurgation using this, I am guaranteed to get minimum distance equal to that odd. If H had odd minimum distance, I am guaranteed to get minimum distance of d min plus 1, because what expurgation will do is it will get rid of odd weight code word. Now, if your H matrix was such that, let us say, hypothetically, let us just assume that weight distribution of H was something, let us just assume, let us say A3 was 4, A0 was 1, and let us just assume A6 was 3. Let us say we had some codes or something like this, right. So this is an odd weight code word, right. If this gets removed, then of course your minimum distance is 6, because you did not have any code word of weight 4. Okay. So that depends on the weight distribution of this, but typically you would not have, I mean, like if you look at code weight distribution, you will have code words of all weights, I mean like 0, 1, 2, 3, I mean at least beyond the minimum distance you will have code words of all weights. So you will have, after 3 you will have 4, 5, 6. That is why I am saying that minimum distance is at least 1 plus 1, but if you have something of this sort, then minimum distance should be 6. But typically you would, I mean, if you look at the minimum distance, I mean distance profile, typically you will have code words starting from dmin plus 1, dmin plus 2, dmin plus 3. So you will have like this. So that's why it's more likely you will get basically if the h has odd dmin, you will get dmin plus 1. So this is expurgation. Okay. Next one is the final thing that, I mean, there are other techniques also. I'm not talking about things like lengthening, puncturing. I'm just giving you one more, which is called extended code. So if you have an nk code, we define a new code in this fashion. So we are adding a new row and we are also adding a new column. Now when you add a new column, and okay, first of all, will this column be independent of other columns? We put a 0 here and we put a 1 here. Okay. So you can show basically the new dimensions of this will be, so number of columns will be n plus 1, and again in case of Hamming code or this thing, none of the rows were all ones. Okay, so when we add an all one row, we are actually increasing the dimension of this h1 also. So this new code, so this, since the parity check matrix Hamming code does not have an all one vector in any of the rows, any linear combination of the last row will never read a all 0 vector. So all rows are linearly independent. So row dimension is n minus k plus 1 and number of columns is n plus 1. This is the dimensions of the H matrix. So the dimension of C1 is basically k. So this is a n plus 1 k code. So what we did was we kept the number of information bits same, but we added one parity bit. And what is that parity bit? Again, you can go back and do VH transpose should be 0. You will get a condition that this code will have all even code words. Okay. Same thing, since the last row is an all one code word, inner product of any odd vector code word with all one code word is 1. So that is not possible. So this extended code only has even weight. So for example, if you want an 8-4 Hamming code, you will use this method, which is extension. Now minimum distance is 4 in this case, if we are using H matrix of Hamming code, because our last row is all 1. Okay. This is one example. Yes.
Some more competitions
Yes.
few more you were saying.
Yeah. So there are six operations. So shortening, opposite of that is lengthening. Then there is puncturing. So there are various operations like that. I just thought I'll just leave you with few. One of the most common thing which people use is puncturing. Maybe I can define that, because in puncturing basically you kind of get rid of parity bits. So if you have an NK code, okay, you try to increase the transmission rate by getting rid of some of the parity bits, especially like in when you are using convolutional code, because that you will see in the afternoon session. In convolutional code, the trellis complexity or decoding complexity is proportional to exponential in k, basically number of information bits. So if you want to get rates such as rate 2/3 convolutional code or rate 3/4 convolutional code, many times they start off with a rate 1/2 code and get rid of some parity bits to get higher rates. So for example, if you have a rate half code, so in rate half code what you will have is, so let's say this is my information bit u1, 2, u3, u4, let's say. So let's say this is my rate half code. So for this information bit, I have this parity bit. This information bit, I have this parity bit. This information bit. So this is a rate half code. Okay. Now, in puncturing what you do is you get rid of some of the parity bits to increase the rate. Let us say I ask you that I want a rate 2 by 3 code. So, for 2 information bits I want only one additional parity bit. Then how will you do it? What you can do is you can send this information bit, send this information bit, and then send maybe one parity bit. So, I do not send this. Then next I send this information bit, I send this information bit, I send this parity bit. I do not send. This is known as puncturing. I am puncturing, I am not sending all the bits. So, like that there are other ways of changing. So, look, I had here k was 1 and n was 2, I changed it to k 2 and n 3. So, if you have any questions, I will be happy. Yes.
Puncturing only parity bits or message bits?
Okay. If you look at classical definition, okay, puncturing was initially defined for parity bits, but nowadays we loosely use it for anything, for deleting anything. So, you will also see, like when we are removing information bits also, you will see people use, loosely using the term puncturing. But if you ask, like classical definition of how puncturing was defined initially for getting rid. So, to increase the rate they basically use it, but nowadays like, because if you delete some of this information bit, then essentially you are actually your rate can go down. But what I am trying to say is you can even also use, like nowadays people use word puncturing for deleting even this. So, if you want rate 2/3, you could also do this, could have done that. I just have to send three bits corresponding to like 2 information bits. So, I could, nowadays you will also see people using this. So, let us see, this is U1 and P1. So, here also if you see period of 2, for 2 information bits I am sending 3 coded bits. For 2 information bits I am sending 3 coded bits. This is also rate 2/3. You will see people are, nowadays people loosely use this also for puncturing, but originally when they defined puncturing they just said sending only, removing only the parity bits. No, we are not losing. So, basically in some cases so these are systematic bits, right, information bits. So, typically if your information sequence has low weight, the same low weight gets carried in your overall code word. So, in some applications you might be able to generate your parity bits which have better distance profiles. So, in some cases you may do better by getting rid of some of the.
So, when we compress, the output of the compression is loosely independent, peers like IID. Otherwise, we would have compressed it more. So, in that case, it will not make sense that we have already compressed the data.
No, so basically what I am trying to say is, so if you look at a code performance, you are looking, a code performance is very much dependent on the distance profile of the code. Okay. Now, look at systematic versus non-systematic. In systematic, the k bits exactly appears like this, and then you have n minus k bits, these are parity bits. Now, just consider a scenario where your input has very small weight, let us say all one sequence, just or not all one sequence, just weight one sequence. Okay. Then those k bits in the code word are actually not increasing your weight, you only get weight 1 from those k bits. Only from this n minus k bits you are getting whatever weight you want. Eventually, when I send the code words over the channel, I want these code words to have high minimum distance. Now, as opposed in the non-systematic case, because I now have k bits to work with, because I can have any linear combination of that. So, potentially I can you can actually create code words which have better distance profiles. So, typically non-systematic, if standalone, especially for a convolutional code, standalone non-systematic has better distance profile than a systematic. But in the newer codes like turbo codes and all those things, there we use systematic code, because for the iterative decoding algorithm, it is better to have those information bits to get started. But if you go back and look at the era before turbo, most of the, especially for the convolutional codes which were used, most of them were basically non-systematic codes which were used, because they, for the same rate, potentially you can get better distance profile. The reason being, as I said, if you have an nk code, for the systematic, the k bits are exactly as the input. So, you have only n minus k to play around and increase your distance profile, whereas in non-systematic, you can have any linear combination for those n bits. So, potentially you can get better distance, and in coding we are worried about separation between the code word, because that determines our performance. Okay. So, this is also of interest, like doing something like this. In fact, this is known as partially systematic, because systematic has all the bits appearing. Here there are some bits appearing, some are not appearing, and if I just delete all of these bits, then it becomes a non-systematic, because I am only sending parity bits. Okay. So, there are some very good codes which are partially systematic also. So, there are other techniques like yes, 1 second. So, you just look at just opposite of each of them. So, shortening would be lengthening, expurgation would be like increasing the, so in expurgation you get n k minus 1, there is opposite technique where you add code words, so you get n k plus 1. Okay. I am just trying to remember, I am just, I will just tell you, I am not remembering at the moment. Okay. And similarly, you have shortening, the opposite of shortening is lengthening. Expurgation, so what would be the thing that you are augmentation? I think that is augmentation, but I will check the name. So, that would be opposite of expurgation, there you actually add like code words.
Is that available in the video link?
No, there is not there. You look at book by Vera Plus, this discussion will be there. There is once, I think one chapter, some section of that. The book, the last book that I had, Huffman and Vera Plus, that would have discussion on this. So, as I said, that is augmentation, I think, if I remember correctly. So, in that, here we are removing some of these code words, there we are actually adding. So, if you have even weight code word, you can add odd weight code words also. Any other question? Okay.